All right, I'm Joe Mike Milley. This is a Group A7 in EECS 203, Winter 12, and we'll be talking about quantified logical expressions, predicates, quantifiers, and English translations.
First, we start with a proposition, the basics. Propositions are statements that have a definite truth value. Examples are 3 is greater than 5, 4 is less than 5, and the deck is blue. We notice that 3 is greater than 5 is false, but is still a proposition because it has a definite truth value. Let's consider the two propositions. P, the ball is wet, and Q, the ball is slippery. We'll throw in not P, which is the ball is dry. Given propositional statements, we can apply propositional logic using operators such as and, or, not, the conditional, the biconditional. There are other operators, but here those are some examples. If the ball is wet, then it is slippery. If P, then Q. This is your classic conditional operator. We can also form a tautology here, which is it is not the case that the ball is wet and dry. Not P and not P is true because P and not P is false. However, there are certain complex logical situations where propositions just do not suffice. We consider statements with a variable such as x is greater than 5, x plus 3 equals 10, or x equals 1. The free variable x in these expressions make it impossible for it to have a definite truth value until we make some restrictions or assign a value to x. Also, these complicated sentences are cumbersome to work with in propositions. All athletes that compete on the collegiate level cannot get paid for performance. This has a truth value. There are clearly propositions inside of this compound statement, but we have difficulty expressing this with only propositions. This is when we use propositional functions with quantifiers.
And to help introduce that, I will introduce my man, Chris Runner.
I'm Chris, and I'll be talking to you. In a logical problem, the domain contains all the possible values of x. X can represent anything from numbers to prepositions or even physical things. For example, x is the set of all athletes.
We can then let the propositional function p of x equal x plays at the collegiate level, and then let q of x equal x cannot get paid for performance. We now have a logical statement: if x plays at the collegiate level, then x cannot get paid for performance. However, we have not done anything to bound x. We have not given it a value or anything we can use to turn that into a definite truth value.
When a domain is applied to a prepositional function, the function must either be true or false for each x. Prepositional functions are useful for making logical statements about an entire domain. In order to write these functions as logical statements, we need to use quantifiers. Quantifiers allow us to turn a prepositional function into a preposition by giving it a true or false value. Examples of quantifiers include for all, there exists one.
We should not let this list of quantifiers limit us. We could also do something like there exists 2, or there exists only 3. There are many quantifiers. We have just chosen to list the important ones and find that it is best to rephrase your question or rephrase your statement so that it only uses these basic quantifiers.
In this example, we use quantifiers to take the prepositions x is incorrect and x is in the first draft of a project to make a singular preposition. There exists an x, where if x is in the first draft of a project, then x is incorrect.
Hi, I'm Jarrett Parker, and I will be talking about negating quantified expressions. The rules for negating quantifiers are called De Morgan's laws for quantifiers. And if you have a statement that for every x, p of x is true, the negation of that would be equivalent to there is an x for which p of x is not true. And if you have a statement, there is an x for which p of x is true, and you negate that, then you have that for all of x, P of X is not true. And a example of a negating quantified expression would be every student in your class, every student at the University of Michigan has taken a course in logic. The X would be that has taken a course in logic, and the domain would be every student. The negation of this statement would be that it is not the case that every student at the University of Michigan has taken a class in logic. This negation makes sense because if you state that every student at the University of Michigan has taken a course in logic and you find at least even one student that hasn't, then...
Yes, that's right, one. We only need one. There needs to exist at least one X, such that someone goes to the University of Michigan yet has not taken a class in logic, and that will make the negation of the for all statement that we had previously. Let us now test our understanding of domains and quantifiers. The domain of X will be all basic geometric shapes. We'll let P of X be X is in the black rectangle, and Q of X be X has a yellow border. What is the truth value of there exists an X such that it is not the case that whenever X is in the black rectangle, X has a yellow border? The answer to this, of course, is false, because every basic geometric shape inside of the black rectangle has a yellow border. The only thing that does not have a yellow border are the letters X, L, M, and N. They have a red border, but our domain does not include letters. It only includes basic geometric shapes.